I'm just trying out various options. Otherwise, that's it. Otherwise, looks like what we have is all right. No, this doesn't work.
Good afternoon, Professor Somak. I think.
Hello, hi. I can only see you. Yes, hello.
Yeah. Hello, sir. Good afternoon. Yeah. So, Srinath, we can actually start now. It's almost.
Yeah, we can start.
Srinath, are you there?
I think he's muted.
Give me a moment. I'll just start streaming and then.
Sure. Yeah. Fine.
So, Dr. Ajit, you can start the meeting now. Dr. Ajit, you can start.
Yeah. Okay. So, good afternoon, everyone. We have a very distinguished scientist and scholar, Professor Somak Chowdhury. Director, Inter-University Center for Astronomy and Astrophysics, commonly known as IUCA, and Pune, for today's colloquium for celebrating Nobel Prize in Physics 2020. It is my proud privilege to welcome Professor Somak Chaudhary to today's webinar. Welcome you, Professor.
Thank you.
I also welcome my colleagues, MSc students, BTech students, PhD scholars, and all others present in this room. Now I request Dr. Srinath to introduce the speaker. Before Srinath, there is a small request. I request all of you to mute the mic except the one who is presenting. And you can write the questions in the chat box. And towards the end of the talk, we will be coming back to the questions. Thank you. I welcome one and all for this colloquium. And I request Srinath now to introduce the speaker.
Hello, everyone. We have today a very distinguished speaker, Professor Somak Raychaudhury. He is the director of Inter-University Center for Astronomy and Astrophysics, Pune. He did his graduate degree from Presidency College, Calcutta, after which he went for higher studies in Oxford University. He did his PhD at Cambridge, from where he moved to Harvard Smithsonian Center for USA. There, as a postdoc, he was part of the team which developed Chandra Observatory for NASA. After his postdoc at CFA, he served as a Birmingham University, UK, for about a decade. From there, he moved to Presidency University as the head of physics and dean of sciences. Since the last 5 years, he has been the director of IUCA. He is also a distinguished fellow of National Academy of Sciences, Royal Astronomical Society, and Astronomical Society. His research involves a wide range of topics ranging in cosmology and astrophysics, from ground-based as well as space-based observations. It is indeed a great privilege to have you here, sir. Over to you.
Thanks very much. Thank you, Srinath, and thank you, Dr. Ajit, for introducing me. I hope I'm audible. There seems to be some disturbance on the line, so if there's any problem, please let me know. And I'll try and let me just see whether there is an issue with the
Hello, Srinath. I think there is some problem.
He seemed to have lost the connection. So let's.
Yeah, we just wait for. Yeah, he was connecting to Wi-Fi or something. He was trying.
Yes, yes. Professor Somak?
Yes. Am I audible to you now? Somehow.
You are now audible. Yes. But you need to share your screen again.
Yes, I will do that now. Yes. I think something happened and my connection dropped, and I will do the whole thing again. Now, am I back to my first slide?
Yes.
Good. Thank you very much. I'm very sorry for this this interruption. I'm not sure what happened, but this looks like it's now working. Okay, so and thanks to everybody for attending this talk. I mean, I'm very happy to talk about this year's Nobel Prize, and I'm going to talk about half of this year's Nobel Prize because I have another talk on the other half later on. But it is also a great pleasure for me that nowadays astrophysics is a subject in which the Nobel Prize is being awarded. As you know, initially what had happened was that in Nobel's original will, Nobel was an engineer himself. He had asked for the Nobel Prizes to be given for applicable sciences, and as a result, initially for many decades, and subjects in which people about the universe about Nobel Prizes. So that is, I think, a welcome change, because what happens in subjects like ours, like in astronomy, is that often, even if you go by Nobel's original idea of the prize being for applicable sciences, a lot of applicability eventually results from the work that is done. I mean, the phone that you have in your pocket, like in astronomy, you're actually seeing the phone, this talk on your phone right now. Almost every element there has come out of some research that was originally theoretical, and many of them were for astronomy. Your digital camera came from astronomy, and so on and so forth. So at the time of doing the research, it is hard to predict what's going to happen later on. Here, the Nobel Prize went to Roger Penrose, a father figure in theoretical astronomy on black holes, and you will hear Professor Kaur talk about this, his work. I'm going to talk about black holes in general, and talk about a little bit about the other half of the Nobel Prize, which is the discovery and finding of black holes in general. I hope this is only the first prize for finding black holes. There are many more to come. And Reinhard Genzel and Andrea Ghez looked at the black hole in the middle of our own galaxy. There are quite a lot of other similar discoveries that I'm sure will be rewarded with the Nobel Prize later on. Now, black holes get I'm assuming a lot of people here know about black holes, but because the expected spread of interest and expertise of the audience is quite large, I thought I'd start from the basics, and this might, some people might think that that's too simple, but please bear with me. I will start from the beginning. And the other thing I want to do is also to make sure you realize that black holes are often portrayed in the common, in the media and in science fiction and in films, etc., as very dangerous. And they're out to get us and things like that. And really, I hope that at the end of this talk, yeah, I can convince you that they aren't really not that dangerous unless you go very near them. They are nice little, very interesting things to study, and has a wonderful effects. But the general impression is that they are really out there to get you. I have to start, in order to understand black holes, from a classical view of black holes. And the place, of course, to start is from the definition of gravity, as was given by Isaac Newton more than 300 years ago. And this, everybody here knows, and it's introduced to us in school, but often in school we are not told that that's not the whole story. And what Newton told us, of course, something we learned in school, as was given by us. It is everything has gravitation. If you have mass, you have gravitation, and it's a property of a massive object. And if you have mass, you exert a gravitational force on something else that has mass, and the force acts along the line of sight that joins the two masses, and it leads to an acceleration of force. It leads to an acceleration which is proportional to the mass of the object that is pulling you, and is inversely proportional to the square of the distance of you. If you are the object of this force, then the distance between the center of mass of the other object that's pulling you and you, right? So, for example, if you're standing on the Earth's surface, the Earth is pulling you and keeping you on the Earth, then this r would be the radius of the Earth, and m will be the mass of the Earth. Now, this leads to a notion of escape velocity, which also we learn in school, and that is because of the gravity pulling you. This means that if you want to escape from this object, escape from the effects of gravitation, you need a minimum kinetic energy, which translates into a velocity that would help you get away from the effects of this force. And so this kinetic energy has to be equal to the potential energy that's associated with the gravitation. And so this leads to this escape velocity, which is a very simple expression that we learn in school, and that is proportional to square root of m over r, right? So that's the idea. So higher the mass of the object, the harder it is to escape from, smaller the object for the same mass, etc. So now one could understand black holes from this notion straight away, if not completely quantitatively, at least qualitatively. And the idea is that if you now know, of course Newton did not know this, that the speed of light is the highest speed you can attain, then if, for example, your escape velocity is equal to or greater than the speed of light, then what will happen is that from this object, nothing can escape. And if nothing can escape, then that is an object from which nothing can escape. Even light is called a black hole. Now, the black hole name came much later. It came in the 20th century. Even in Newton's time and afterwards, people realized from his theory that such things could exist. They called it different things, dark stars, for example, black stars, and things like that. Now, the question is, how can you turn something into a black hole? You have to play around with this equation and see that if you want this escape velocity to be higher than the speed of light, you have two parameters to play with. You can either have things with the same radius, but increase their mass. And so as the mass increases, if you throw up something, for example, you try to escape from this object, then you don't get very far away. And if the mass increases, your maximum height gets lower and lower and lower, etc. And you need more velocity to escape from it. Now, in a physical sense, it is hard to actually have a situation in which you have something for which the radius is the same, but the mass increases. So a more realistic situation is the opposite. What you do is, because it's gm over r, within the square root, you can keep the mass the same, but decrease the radius. And as you make things smaller and smaller and smaller, density increases. But what happens is that velocity, escape velocity, also increases. And classically, this is the way to understand a black hole. If you can take something and shrink it to a size such that light cannot escape from it, then that is a black hole. So this also means that anybody, anything that has mass, including you and I, can turn into a black hole. Now let's see how difficult that is. And of course, as a result, just after Newton actually told the world about gravity, people started thinking about these things. As you can see, at the end of by the end of the 18th century, people had already thought how you could take something like the sun and make it smaller, or a star and make it smaller, and such that it becomes a dark star, such that light can't escape. John Mitchell paper is supposed to be one of the earliest papers. And of course, Laplace's name is everywhere. I mean, this man was very smart, and he also had thought about such things. Now, if you look at what kind of velocities we are talking about, normally an escape velocity from the Earth is about 11 kilometers per second. And so this is one of the reasons why when we actually launch rockets that have to go to the moon or to Venus or whatever, even ISRO does not launch rockets at 11 kilometers per second. It's very hard. It's quite a high velocity, 43,000 kilometers per hour. And this just means that when we launch rockets, we launch them in stages such that they go to a certain height above the Earth's surface, and in this orbit, they will get to a phase where the escape velocity is lower because that R is even higher, and then fire enough rockets to break free of the gravity.
Hello.
I think again, Professor, connection is some problem.
Srinath,
Yes,
this is Partha. Are you recording it?
I am recording it.
Maybe because of this record thing, I think it's there could be issue with the bandwidth.
But none of us have an issue, right? So
Yeah, but normally I think it's not very clear. Maybe the speaker can use a headphone or microphone.
Somak,
Yeah, I dropped out when, what time did I drop out?
you were talking about breaking free of gravity.
Okay, right. I don't know what's happening though. I mean, what?
Srinath,
Yes,
I think there's some issue in Ayuka, looks like.
problem.
I think the professor is trying to connect through Wi-Fi, not through LAN. That may be one reason. Yeah.
Srinath, maybe you can tell the speaker to use his own phone Wi-Fi instead of the institute Wi-Fi. I don't know what kind of Wi-Fi he is using.
Should we just tell him that he's dropped off, and otherwise, whether he knows that now? I don't know.
I think he doesn't know it.
Hi,
Maybe Srinath can. Yeah.
am I back?
Yes, yes, no problem. Please. Yeah.
Okay, can you hear me now?
Yeah, sure.
Yes, yes.
Yeah, I changed the connection, and maybe it's at my end. I don't know yet because I've been giving a talk and teaching every day, and this has never happened. Okay, so let me share this again and see where I'm going. Okay, can you see this now?
Yes.
Okay, so I think, around here, but maybe the slide before, doesn't matter. So I was introducing the subject of what you do is I said that in order to make something into a black hole, anybody that has mass, you have to shrink it to a size that from which light cannot escape. Now, in order to calculate this, one cannot really use Newton's formulation of gravity. One uses a formula like this, which comes directly from Einstein's formulation of gravity, which I'll talk about in a minute. And this is known as the Schwarzschild radius. And so something that has mass, very simple formula again, 2gm over c squared. C is the speed of light. If you shrink something to that radius, then you, at least that radius, that is, then the escape velocity from its surface becomes a speed of light or more. And thus Earth needs to be shrunk to less than a centimeter. And the sun, for the sun, that radius is about 3 kilometers. Now, you can see that coming up with a process where the Earth shrinks to less than a centimeter is very difficult. I mean, sometimes when at CERN the LHC is turned on, people say, oh, the Earth is going to turn into a black hole and stuff like that. And you can see how ridiculous that is. But stars shrinking to a size like that has been shown to be possible. And this is where we get into the realm of astrophysics. So the idea is that to then quantify this, one needs to go beyond Newton. And this is what Newton said. And Einstein realized that Newton's theory of gravity is incomplete. And what happens is that once you get to very high masses or very high velocities, then it leads to certain inconsistencies. If you're thinking of the gravity being a force which acts along the line joining, it's like an invisible string, joining two things. The things are moving very fast. One of the questions is, how does anything know where that force is coming from? Because, if the force is acting along the line joining the two, then you need to know where the other object is. And if they're moving very close to the speed of light, that kind of information needs to be exchanged at very high speeds. In Newton's case, that didn't have a problem because for Newton, information could travel at any speed, whereas Einstein essentially showed at the beginning of the 20th century that nothing can travel faster than the speed of light. No information can. So Einstein realized that in order to explain gravity, you'll have to make it into a very local effect, which means that gravity has to be a property that is very local. And so he essentially said gravity is not a force. It just means that if you have mass, what you do is you distort space around you. And for space, one uses the word space-time because space and time are related. It's one thing. In Newton's theory, there is no space. It's vacuum between the stars. Whereas in Einstein's formulation, the universe is the fabric of the universe is space-time, and that space-time is distorted by matter. And then other things are move along this curved space-time or distorted space-time along trajectories that are optimal, and thus you orbits of things that are given by the shape of space-time. So here you are. So if you have the Earth moving around the sun, say the sun has locally distorted space-time, and the Earth is then trapped in that curvature of space-time and is moving in that trapped curvature along the most optimal path, not because there is an invisible string that's connecting the sun and the Earth pulling it, but it is an effect of gravity, that the mass of the sun, the mass changes the shape of space-time, and then the space-time tells the object how to move in that space-time. Right? This also means that light can also be curved, light's trajectories can be curved. In Newton's theory, light has no mass, so it cannot be curved by gravity, it cannot be affected by gravity. In this particular case, it doesn't matter whether the photons have mass or not. Photons follow the geometry of space-time, and if the space-time is curved, light also is curved. And this is how Einstein's theory was first established, by looking at curved light from stars behind the sun, and looking at the effects of that. So that's the idea. So we needed the formulation of Einstein in order to quantify how things will behave around these black holes that we're talking about, which are very, very compact objects, which are very small but have a lot of mass, and the velocities that are involved are pretty high as a result, because you look at kinetic energy of things that are escaping from black holes and things like that. So he worked out this theory in 1915. Carl Schwarzschild, within a year, had solved Einstein's equations within a few months, actually, of it being published. Einstein's theory was published in a German journal in the middle of the First World War, when Germany was at war with the rest of the world. And so it took a while for it to be known to the rest of the world. But Germans had a head start. And Carl Schwarzschild was actually part of the German army fighting in Russia, in Russian front. And he had a copy of Einstein's paper with him, and he found this solution in which is a description of the space-time around a compact object, or any spherical symmetric object, and which is now known as the Schwarzschild metric. And he'd written it in a piece of a postcard and sent it to Einstein, and then he died in the war. And Einstein published it posthumously after Schwarzschild's death. And we look at so many consequences of the Schwarzschild metric now, and one of them is very simply finding out the radius of a black hole. Now, still there was the problem of how you can turn something into a black hole, and that to us a little later than that by Subramanian Chandrasekhar. Chandrasekhar in the 1930s essentially was worrying about just this thing about what happens when a star collapses. Chandrasekhar, as an undergraduate, would visit his uncle, C.V. Raman, in Calcutta, working at the Association for Cultivation of Science, where he had copies of the Astrophysical Journal, and he realized that this is a very alive astrophysical problem. He also was aware, even as an undergraduate at Presidency College Madras, that this new theory called quantum theory was being proposed. And so he brought the two together. He also went to do a PhD with Dirac himself in Cambridge. But in this process of thinking about stars and working on quantum mechanics, he applied quantum physics to the stars and realized that as a star collapses at the end of its life, by life I mean at the end of the time when it stops fusing nuclei in its center to produce energy, when it runs out of fuel, it has to collapse, and then it goes through various stages, and certain stars can turn into black holes. There's nothing to stop them from collapsing to a singularity. That's the singularity meaning it collapses beyond all kinds of forces that are there, quantum mechanical forces, to stop something collapsing. And you'll hear about the singularity when you hear about Penrose's work later on. But the idea of Einstein then in this scenario is that space-time around a black hole is so distorted that even light cannot climb out of this well. And this is why I think John Wheeler called it black hole. There are these myths about black holes that I want you to be aware of. They don't go around in essentially vacuum cleaning everything around us like a lot of science fiction would have us believe. In fact, our sun is not going to turn into a black hole, but if it did, then you would be surprised if you haven't thought of it already that most of the planets are going to go around this black hole in its normal orbit, nothing's going to happen. They're not going to all fall into the sun, like a lot of science fiction tells you. In fact, the gravitational influence of a black hole doesn't go much beyond out to, for example, the distances of the planets that there are in the solar system. So, of course, the world will be a very dark place if the sun turns into a black hole, but we're not going to fall into it. So that black holes aren't dangerous enough that they are out there to destroy other things. So what Chandrasekhar essentially told us was that when stars die, at the end of the star's life, when it stops the fusion, the production of energy in the middle of a star, and a star is essentially a ball of plasma, which has this equilibrium between the production of energy in the middle, which causes thermal random motion of its particles, which balances the gravity, the thermal pressure balances the gravitational pressure of the entire mass. Otherwise, it collapses. And once this fusion reaction in the center is finished, because the fuel is over, then there is nothing to stop it from collapsing. And as a result, the star collapses. Now, our sun, which of course is less than this number, which is called the Chandrasekhar limit, a number that is 1.4 times the mass of the sun. Our sun is, of course, less than that. Will end up in something called a white dwarf. And if it's slightly more massive, but up to about, say, 3 or 4 times the mass of the sun, then the outer parts of the star expand, explode into a supernova, and the inner part collapses to form something called a neutron star, which is about 10 kilometers across. It's almost entirely made of neutrons rapidly spinning. This is standard astrophysical lesson that I'm not going to give you now. But the idea is that more massive stars that are much more massive than the sun, even 3.5, 4 times the mass of the sun, would explode after the end of its life, but the inner parts would collapse if they are at least about 3 times the mass of the sun, into something that will have nothing to stop it. The quantum mechanical forces, the degeneracy pressure that would stop a normal star going into a white dwarf or a neutron star does not work anymore, and so this star is then going to collapse into something that's much, much smaller, and then reach this quantity, which is called the Schwarzschild radius, and go beyond that. And as a result, the escape velocity from it will become more than the speed of light. This is how you create a black hole. So, and the space-time around it is going to be very seriously distorted, such that things that are falling into a black hole will not be able to come out in even light. That is the idea. And so this is what a black hole looks like. So black hole's close-up picture is black, because we see things essentially because of light that comes from something, either reflected light or light that comes from within that object. And that's essentially, by light I mean any kind of radiation. And that's the astronomers' way of finding these things. And if nothing can come out of a black hole, then you cannot see a black hole. And this is why till the 70s and 80s, even people like Stephen Hawking were betting others, saying that we will never find a black hole. And yet I'm here giving a talk called Finding Black Holes, and this year's Nobel Prize is about finding a black hole. So there are these different kinds of black holes. As you know, we have the stellar mass black holes, the ones I talked about just now, which come from the collapse of stars. Now, the most massive star that we know of in our own galaxy is about 100 times the mass of the sun. So typically, these stellar mass black holes would be much less than that, because some of the mass of the sun will go into the supernova that explodes. Then we also know that there are a lot of supermassive black holes, these black holes that are in the middle of a galaxy. There's one per galaxy in the middle of a galaxy, and this is the subject of this year's Nobel Prize. And these are typically 10 to the 6 to about 10 to the 9 times the mass of the sun. And the idea is then there are these things in between that have to be there, which have been debated for a long time, but now in the last few weeks, we have found direct evidence of black holes that are in the mass range in between them. And the idea is, why should they be there? First of all, why shouldn't there be? Why should there be only two types of black holes? But of course, we don't know how these supermassive black holes are formed. And one of the scenarios is that the stellar mass black holes would be merging with each other hierarchically to form bigger and bigger and bigger and bigger black holes till they reach 10 to the 6 to 10 to the 9 or whatever. And in the center of the galaxy where matter falls in, that's the place where most matter would fall in. But then you expect to see the black holes that are in the middle, 10 to the 4, 10 to the 5, 10 to the 3 times the mass of the sun, and you don't see them. And only recently, we've just announced 140 solar mass black hole that has been discovered from gravitational waves, which I'll mention towards the end. So our own galaxy then looks like this. As you know, we live in the Milky Way, where we are a planet around the sun, which is roughly about 25,000 light years, 8 kiloparsecs from the center of the galaxy. And we're looking at the sky through the screen of stars that are here. And if we look towards the middle of our galaxy, and that's where the supermassive black hole in the middle of our galaxy is, we would see it as a band in the sky, right? This is, again, artist's impression. You can't really take a picture of our own galaxy from within it. So if you're looking from here towards here, you would see a band, which is called the Milky Way, which is not very well seen from India. It's much, of course you can. If you go to a very dark place, you can see actually some fringe of this and also the other part of the Milky Way. But to look directly towards the center of our galaxy, the best seen south of the equator, if you go to, for example, this is a picture taken from Chile. The telescope in the front is the 4-meter telescope in Cerro Tololo, which is now the Dark Energy Telescope. And you can see that what you're seeing here is a view from here towards there. There's a lot of dust in the plane of the galaxy, and that dust comes from the material that didn't get into the stars as they were being formed, and so a lot of this matter also comes out of stars. But by dust I mean it's basically solid hydrogen, but also has components which are more complex molecules, including what we call dust, silicon dioxide, things like that. And so this is cold and much colder than the stars themselves, a few hundred degrees, and some of the dust is hot. But what this dust does is it blocks light. And so if you're looking at the center of our galaxy, which is here, which is where the supermassive black hole is, you can see, and that's where it is. And that's not the black of the black hole, it's the black of the dust blocking its surroundings. Now, one of the ways of trying to detect that black hole is to look at the dynamics of stars around them. And if you want to do that, you really can't see, as you can see, because the light from the surroundings of the black hole is blocked by this dust. And so what you have to do is what these two people did, for which they got the Nobel Prize this year. Andrea Ghez and her group working at UCLA, they used the Keck telescope, which is the 10-meter telescope, the largest telescope now in the world, on Hawaii. And Reinhard Genzel started actually before Andrea Ghez, as early as 1991. And he eventually used the very large telescope not far from the telescope I showed you in La Silla. And both of them looked essentially here, but looked in the infrared light. It looked not near infrared, about 2 microns. Our visual range ends at about 0.8 microns, 800 nanometers, and they looked at about 2 microns, and their cameras were sensitive to 2 microns. And they also had to do another thing, and that is as follows. So here you are, you're looking at the middle of the Milky Way, and you're looking at the supermassive black hole. One of the major problems in observing near the black hole, even if you can see through infrared light, is the fact that the atmosphere blurs the light. And so this is known as seeing. What happens is that all light has to come through the atmosphere, and the various layers of the atmosphere have different temperature, pressure, and density, and that varies on the time scale of fraction of a second. So what is happening is that the light is coming through a medium which has a variable refractive index as a function of t, and that's varying very rapidly. And as a result, it comes down and lands on your detector. It could be your eye, could be a detector, a camera, and that image moves around. And this is called twinkling. That is why stars twinkle. And as a result, if you take an image that is a few seconds or a few minutes or a few hours long, then you get a blurred image. And if you want to see the stars very near the black hole, you need exquisite resolution better than a second of arc, has to be about 1/10 of a second of arc. And this is not possible with normal telescopes. Both Andrea Ghez and Genzel worked out this idea of using adaptive optics. And this is something that I'm very proud that IUCAA has a wonderful program in adaptive optics. What you do is that you have a mirror. The mirror of the telescope itself is built such that nowadays everything can be computer controlled. The shape of the mirror itself changes in real time and in every fraction of a second, such that it compensates for the change in the trajectory of light coming through the atmosphere. So you have another telescope that looks at a star and sees how the speckle moves, the image moves, and feeds that information into the much larger telescope. And what it does is that it changes the shape of the mirror such that its focus stays absolutely perfect. And this is something that they had to employ. This was the project for which adaptive optics was one of the most important things that was done. The Keck telescope has 72 mirrors, each about a meter big, making a 10-meter surface, and each one can be moved independently of each other so that the shape of the mirror can change, and as a result, the exquisite resolution is obtained. So this is why you get the Nobel Prize. You don't get the Nobel Prize for a smart idea and drawing some graphs. You have to work for, in the case of Ghez and Genzel, they spent 25 to 30 years of their life developing the instrumentation for it and slowly improving their resolution so that then they started seeing the stars around the middle of the galaxy. So normally you look in the middle of the galaxy. This is the galactic center at 2 microns, and without adaptive optics, if this is your essentially the stars around the center of the galaxy, this is where the black hole would be. It's all blurred, but this is what they got. So what they got, and you've seen this, I'm sure, many times, that right from the beginning of the 1990s, these are actual real images of the stars around the center of the Milky Way. This is where the black hole is. You won't see the black hole, but all you're seeing is in projection the various orbits of the stars that go around it, and that's the magic of this whole experiment. So here is a better one. Andrea Ghez's movie of her different stars. All of these stars have names. We all know them personally. They all have, and look, they are moving around in orbits like planets around the sun. The SO2, which is the star of the stars in these stars, has an orbit of 15 years. 15 years it goes around in its elliptical orbit, right? And just like you can measure the mass of the sun, if you know the orbits of the planets, for these orbits of these stars, you can measure the mass of that central object in the Milky Way. So Andrea Ghez's movie starts from 1995, and you can see the year here, and observations every night make these you're looking at the individual stars, and look at the scale. This is 1/10 of a second of arc. And normally, that's the resolution of the Hubble Space Telescope in space. And from the ground, infrared light, they were able to get this kind of resolution when you see the trajectories, the orbits of the stars. And if you want more views of these, go to her website. Of course, there are lovely YouTube videos as well. And Andrea Ghez has a great TED Talk, one of the best TED Talks ever, on this topic, on how to find the black hole in the center of our galaxy, given almost 10 years ago. This is because even when they started in 1995, 2 years, they actually had measured the mass. You don't need to go around the full orbit to know what the orbit is going to be like. And they were competing with each other using two of the largest telescopes in the world. The two groups, the German group and the American group. Actually, the Breakthrough Prize, when it was given a few years ago, was given only to Genzel. And this year, I'm very glad that both groups have been recognized, even though Genzel has written a very snarky article recently in Der Spiegel saying, I should have got the prize and things like that. I don't know why I did that. But I think they both actually had amazingly done this job. In fact, the pictures that I'm showing you are all from the UCLA group. They produced some of the best images that are possible. Now, you can see that in this time of 25, 30 years, many of these orbits have been completed, but you don't need to complete an orbit to know what the orbit is. You can always fit it. And for example, here, you can see as early when you start in 1992, 94, etc., as early as 2002, this is Genzel's plot. As early as 2002, they had mapped S2's orbit very well. And at that time, even in 2002, they had found from Kepler's third law, mapping that elliptical orbit, that the mass that was causing this was 3.5 times 10 to the 6 times the mass of the sun. Actually, now the final result that is quoted is 4 times 4.1. But there you are. So you prove that there's a million solar mass unseen object there. Now, the other kinds of things that have a million solar mass are star clusters, globular clusters. Now, if this were a globular cluster, it would have been much bigger because globular clusters are 10 parsecs in size. Whereas here, you can see these stars coming very close to the unknown object. The perigalacticon distance is 120 AU, which is kind of the size. AU is the astronomical unit, the distance between the Earth and the Sun. 100 AU is just a little larger than the size of the solar system. Certainly not many tens of parsecs. So clearly, this is a very compact object. And so the only thing we know of that would be a million times the mass of the sun at least and have such a small dimension is a black hole. So this is a proof that that's a black hole, as well as a good measurement of the mass. Now, this is not just from S2. You saw all those stars in here. Each of them gives an independent measure. And this is also Kepler's first law, showing you that the thing that's pulling you is at the focus of the ellipse. And you can see this black hole is at the focus of each of these ellipses, one of the foci. And also, it can show you all of Kepler's laws in action. It's great. And also, you can use Kepler's laws because these velocities are not high enough that you need relativistic corrections. As you know, very recently, there has been a measurement of from microwaves of actually the boundary, very close to the Schwarzschild radius of a black hole, the supermassive black hole in the middle of the galaxy, M87. Their group is also trying to make a similar image of our own galaxy's black hole. I'm sure this will lead to a Nobel Prize very soon in the coming years, because this is also a kind of project that has required a huge amount of technology behind it. So I told you about the different kinds of black holes. Do I have another 10, 15 minutes? I'm asking the organizers.
Yes, please.
Okay. So I'm going to talk about, because I've now talked about Gez and Genzel's measurement of the supermassive black hole in the middle. I want to quickly talk about two things. One is, what do you do about the other kinds of black holes, the stellar mass black holes and the mid-sized black holes, and show you where they are, and then end with what the connection is with the future of Indian research in doing this kind of thing. So what happens is that, as you know, that we are not just confined to light in the electromagnetic radiation. Gez and Genzel were using 2 microns, which is a wavelength, which is just outside the limit of the visible light here in what is called infrared here. That's around here. But one can actually go all around the electromagnetic spectrum. And what happens is that if you go very close to the black hole,
things that are falling into the black hole can get very, very hot. And they can be as hot as 10 to the 6, 10 to the 7 degrees. And then they would emit very high energy radiation, which will be in this regime of X-rays and gamma rays, or even ultraviolet. And the first attempt that was made to find black holes was to make to observe in this regime, and not for the supermassive black holes, but the stellar mass black holes, because there'll be gas falling into these black holes. The only problem is that the atmosphere doesn't let through light across this electromagnetic spectrum. Only the optical window, and you can see there's a window around 2 microns, which Gez and Genzel used. You have to go very high up in the mountains to do that. But in the radio window and optical window, you can have light come right through. But in order to observe in the X-rays, you have to launch your telescope in space. And this is where observatories like the Chandra X-ray Observatory, which I was associated with, comes in. Chandra, the X-ray Observatory, was essentially built to find black holes, but stellar mass black holes. And it was named after Chandrasekhar because he was the person who showed us how to make black holes. And so you can see, in order to have an X-ray observatory do this, you have to put it in space. But the Earth is surrounded by charged particles, which are always interfering with the kind of detectors that you use. So you need an orbit that goes very far away from the Earth in order to observe. And so these are not the optical observatories like Hubble Space Telescope, which are a few hundred kilometers above the Earth. They go all the way up to 100,000 kilometers. It's a 64-hour orbit in which the telescope only operates half of the time when it's far away from, these are the radiation belts that surround the Earth. And you have to switch off everything when you come within the radiation belts and switch on the orbit again and things like that. So X-ray astronomy is a wonderful subject on its own right, which I'm not going to go into right now. But one had to develop this kind of thing to observe from space. And this is why, and this only could happen after you could launch these things, of course. Chandra and XMM Newton, they were launched in 1999, and you can see that is why this is such a new subject. We really had to learn how to observe from space at wavelengths, which are not the normal optical infrared wavelengths that we are used to. For example, if you need to build X-ray mirrors, you have to, for example, build them such that you detect the X-rays at grazing incidence, because if, for example, normal incidence mirrors, X-rays would go right through. You know that from your experience with X-ray machines at hospitals, X-rays will go right through. But for grazing incidence, what happens is that X-rays have wavelengths that are nanometers, which are comparable to the interatomic spacing or intermolecular spacing on the surfaces of these things. So these, for example, are built with metals, with gold-plated, maybe aluminum or steel, and things like that. And so if the plating is gold, then for gold, if it's nanometers, if the particle separation, then grazing incidence means that the effective interparticle spacing is smaller, and so they get reflected. For gold, for example, if it's more than 2 degrees from the surface, then X-rays will go right through. And thus, the architecture of X-ray telescopes is that they are very long, they're cylindrical, they're actually paraboloids, which are long. And the Chandra X-ray Observatory is about 5 meters long, where the X-rays coming through here, and they end up at the instrument at the back there. So this is what we are trying to then observe and compare it with Gez and Genzel's way of looking at things, and you'll see the connection very soon. Half of the stars in our galaxy are in binary systems. You have 2 stars together going around each other. They are unequal, so one of them will evolve first and maybe turn into a black hole. And so this is a massive star that exploded and turned into a black hole. And the other one, it keeps on evolving in its lifetime, but it's now orbiting a black hole. And as a result, towards the end of its life, as it's expanding because it's losing its equilibrium due to its energy generation, you would find that the outer layers of this star will be closer to the black hole than its gravity can hold. So its matter will be pulled towards the black hole. It will start falling on the black hole, and the black hole is then pulling matter from the other star. And because it has angular momentum, it doesn't go straight into the black hole. It makes a little disk, which is called an accretion disk, and this goes on and on and on, and matter slowly falls into the black hole, but the accretion disk stays around the black hole, and this gets heated up because of the gravitational potential energy of the black hole to 10 to the 7 degrees. And with 10 to the 7 degrees, the main radiation from it, even if it were just a black body, would come out in the X-rays. So this is what you observe, and this is an artist's impression of what this would be. That's the black hole in the middle, which you don't see, but we don't need to see it. You see the effect of it, of its gravitational pull, because the surroundings are so hot, they start emitting X-rays, and this is what happens as the other star goes around the black hole in an X-ray binary. It creates this amazing effect of emitting X-rays. And so I just wanted to show you an example. This is Centaurus A, one of our nearest galaxies. This is what it looks like in the optical, and you're seeing optical light here taken from a small telescope on the Earth, and everything that you see in this picture is a few thousand degrees hot, and that is why it emits optical light. These are normal stars like our sun. Since we built Chandra, we had guaranteed time on the Chandra observatory, so we pointed Chandra towards Centaurus A for 2 million seconds in all in the last 20 years or so. And what you do, adding up all that, you get an X-ray image of Centaurus A, which looks like that. So here is, everything is a few thousand degrees hot, and here everything is 10 to the power 7 degrees hot, everything that you see. And what you see as point objects are these X-ray binaries, and many of them are black holes. Some of them are neutron stars paired with other normal stars. I had a student who did his PhD on all these little objects in here, and from the spectrum and variability found which ones of these are X-ray, are black hole binaries, and which ones are neutron star binaries, and some of them are black holes. And right in the middle is the supermassive black hole in Centaurus A, just like the one that Ghez and Genzel found in our own galaxy. And that one is also guzzling gas, but also spewing it out because it can't take as much gas is falling in, it can't retain it, it spews it out, and here's a jet that's coming out of that black hole, traveling close to the speed of light across the galaxy. The galaxy, as you can see, is that big. And so it's coming from the middle. So in this particular plot, you can see one supermassive black hole and loads of stellar mass black holes all around. And this is the general picture. Our galaxy has many, many such. So each galaxy has one in the center, a supermassive black hole, a very big one. The formation is not fully understood yet, but we are getting there. We're trying to understand. And then you have these binary stars in there. And I'll conclude by saying what connects these two. That connects these two, and this is where I think India comes in its future plans in looking at these exotic objects. We have plans for observing the whole sky with some of the largest instruments possible. India is getting into this game now of what is known as, I'll talk about that later, what is known as the mega science projects in physics and astrophysics. India was not part of such projects until a decade ago. Indian science was in individual institutions, in little labs, but now we are part of all this, and the top two are the two which are which we are involved in IUCA, for example, and in which we will in various ways be dealing with new discoveries of black holes. And this is, for example, the 30-meter telescope in Hawaii is just a bigger version of the Keck. I told you Keck is 10 meters across with 72 mirrors. The 30-meter telescope that is going to be built in Hawaii has 492 mirrors across a 30-meter surface. And here, 5 countries are building it, including Andrea Ghez' institution, UCLA. The USA is involved through the University of California and Caltech. And I sit with Andrea Ghez on various committee meetings discussing the TMT. She's one of the major people involved in building this telescope because she has an interest in doing the same thing to other galaxies. finding the black holes and looking at orbits around the central black holes in those galaxies. Of course, this will take 10 years to build, and she might not be operational then, but this is the plan. The plan is that, and India is actually 10% a partner in the TMT, and much of this adaptive optics system that I'm talking about, the control of these individual mirrors, are actually being built in India by Indian companies. The mechanism that moves each of these mirrors, or the 492 mirrors, 100 of those mirrors segments will be built here in Bangalore at the IIA. And between Aries and Nainital and us and IIA, we are building a lot of the mechanism that will go into this. So we are going to get into, and Indian students are going to do their PhDs using this, the largest telescope in the world. And then finally, as you know, the other way of finding these black holes are gravitational waves, for which the Nobel Prize has already been given 3 years ago. But the story hasn't stopped there. The Nobel Prize was given very soon after the discovery of the gravitational waves, and there Indian astronomers have been involved from the very beginning. There were 37 authors actually in the first discovery paper that led to the Nobel Prize. And now we have many other authors from the LIGO collaboration. This comes from the fact that Einstein not only said light bends as it goes around curved space-time. When something moves in curved space-time, it will also cause ripples that will go around, and the ripples will go in the form of gravitational waves. Very soon he realized that the amplitude of these ripples will be so small, they will be smaller than the nucleus of an atom. But we have done it now. We have used the LIGO detectors, and you must have heard of them. I'm not going to talk in great detail here about it. That's the subject of other talks. But I wanted to mention it here because this is directly connected to the kind of things that we are doing for which the Nobel Prize was given. The LIGO detectors are essentially large, very large, 4-kilometer long, large Michelson spectrometers. And as the gravitational wave passes through the fabric of space-time, it shrinks and pulls the fabric of space-time. And so the two different arms, which are perpendicular to each other, are squashed and squeezed in different ways. And so in an interferometer, if you have perpendicular paths of the same laser beam in perfect equilibrium, canceling each other, then that can be that balance can be lost by a gravitational wave passing, and this is how gravitational waves are detected. The 10 to the power minus 18 meters is the amplitude of a gravitational wave that is normally detected by LIGO, and that, as you can see, is 3 orders of magnitude smaller than the nuclear diameter. And it's an amazing thing that such measurements have now been done in the presence of displacements that are much, much larger due to all kinds of noise. The original discovery was made by these 2 LIGO detectors, 3,000 kilometers apart in Washington State and Louisiana. And you know about all this. The detection was, and it found 2 black holes, and these are the Schwarzschild radii of the black hole compared to a map of India, just to show how big these black holes are. And the first pair that was found was about 2 black holes 30 times the mass of the sun, becoming one that is about 60 times the mass of the sun. Now, very recently, we announced this one, where we found 2 things that are 2 black holes 85 times the mass of the sun and 65 times the mass of the sun, merging into something that are 140 times the mass of the sun. And that's led to this amazing picture that you can see. Here's the mass in terms of the mass of the sun, and you can see in each of these LIGO measurements, you can measure 2 black holes merging into a third one. And you can see the entire range of the masses of these black holes that have been found. These are the ones, the purple ones are the ones that are found by X-rays from Chandra and XMM, and these are the ones that are found from LIGO. And you can see slowly we're building up to the supermassive black hole that we found in the middle of our galaxy. So this is what connects the stellar mass black holes to the supermassive black holes. And that's where I should stop. I should say that we are now going to build the 3rd LIGO detector in collaboration with the LIGO observatories in the US. In India, it's going to be built in Maharashtra. And this is a plan of the people who are going to build it. The institutions who are involved, one of them is Ayuka, representing all the universities in India, including your university. And people who are undergraduates and postgraduates now will be able to use LIGO India when it's finally built in 2027, 28, something like that. It's going to become a reality here. So this is what it looks like now, but in a few years, we're going to build it. We are now working with the people in the area, in Hingoli district, trying to talk to the villagers there, the children there, the schools, so that they know that a world-class facility is coming where they are. And I hope, and in social media we are there, I hope a lot of people here will be inspired to read about black holes. And here are some books that you can read and read about Einstein. One of my favorite books is the book by Kip Thorne, which talks about all the issues that I talked about now, and similar issues in a book by Richard Gott. I wanted to stop by saying that this is only the beginning of the recognition of the impact of black holes in science in general. And I'm very happy that this year's Nobel Prize recognizes that. Thank you.
Thank you very much, Professor Somak Raychaudhury. We have a few questions. I'll read.
I'm going to stop presenting so that I can see everybody. Yes, okay, go ahead.
There is Ms. Pavitra Mukundan. She wants to know, why did you tell that sun is not going to turn into a black hole?
All right, okay. So
I
said that because if you remember, I said that I of course didn't go into the details of the physics that went into Chandrasekhar discovering what kinds of things will turn into what kind of compact objects, right? But I gave you the result. The result was that he found that as a star collapses, if it's not being stopped, the gravitational collapse of a star is not being stopped by the constant energy generation in the middle of the star and its effects, which is the thermal pressure, the radiation pressure, and things like that, then it's going to collapse. But there's nothing to stop it. In classical physics, there's nothing to stop it. But Chandrasekhar realized, and this is why I said he applied the laws of quantum mechanics. You all read about the Pauli exclusion principle. You know that the particles that make up the sun are fermions. And so you know that there are very discrete energy levels starting from the ground state up for each of these particles, and no two particles can have the same quantum number. So eventually it will come to a stage where the particles themselves cannot occupy all the states above the ground state, and they can't go into one state like a Bose-Einstein condensation can. And so that has its own pressure. That will stop the collapse of the star. Now, that of course has a finite amount, and then above a certain mass, above a certain gravitational pressure, even that degeneracy pressure cannot stop the collapse, and the star will continue collapsing. And then comes another kind of degeneracy pressure, which comes from everything turning into neutrons, and the neutrons themselves having a degeneracy pressure. So the first one was due to electrons and nucleons, and then you went to the nucleus zone particles and things like that. So there are various levels, and even there, a certain gravitational mass is going to be so produce so much gravitational pressure that even then the neutron degeneracy pressure cannot stop the collapse. Right. So I said that the first of these stages, where a star can collapse and form a white dwarf and stay there, and the limit was 1.4 times the mass of the sun, and you have to be around that 1.4 times the mass of the sun for it to collapse to form a white dwarf. And if it's much more than that, then it collapses further. The sun is less than 1.4 times the mass of the sun, right? And so it's going to stop and be a white dwarf. It can't collapse any further. Its degeneracy pressure will be enough for it to stop its collapse. And that is why the sun is not going to turn into a black hole.
Deepak has a question. Why does the black hole mass gap arises?
So again, I told you that we do not understand that, and that's been a huge debate for a long time. We know that the stellar mass black holes can come from sun, come from stars, but we don't see such massive stars in our galaxy or nearby galaxies. We see the maximum that we see is 100 solar masses. So it can only form things that are less than black holes that are less than 100 times the mass of the sun. And yet we see the supermassive black holes, and we don't know where they come from. And there's been a lot of theories about what that could be. For example, some people thought that in the early stages of the universe, you could form things that are very massive. But then those stars won't last very long. They're gone. We don't see them around now. So they could be remnants of very massive early objects that were formed. There are some people who have theories that such things can form in the early universe as black holes, and they're called primordial black holes. And galaxies would form around them. They would form the seeds of galaxies and things like that. So there are a lot of theories, and this hasn't been resolved yet. But one clue has come, and this is why I took you very hurriedly through the results that have come from the gravitational waves. There's one clue now that you can get black holes, that the gravitational wave experiments are showing us that two black holes can merge to form a bigger black hole. And we now have 75 such examples in the 5-year history of gravitational waves where you have found them. And the most massive of them is 140 times the mass of the sun. Still, there's a huge gap. But at least this is indicating that if we continue looking, we might find this whole kind of ladder of forming with smaller black holes into larger and larger. There are other people, there are very famous people like Martin Rees, for example, who's the astronomer royal in England. He believes that the universe isn't old enough for this to happen. This, for example, for smaller black holes to merge into bigger black holes and make 10 to the power 9 times the mass of the sun. And so there are people who think that they have a completely different origin. So this is not solved yet.
Rakshit Gharat has a question about primordial black holes. He wants to know how are they formed, and can we detect them? How are they related to Hawking radiation?
These are completely different questions. Yes, it's very interesting. Primordial black holes can be more massive. Normally, Hawking radiation is, of course, a quantum mechanical effect that Hawking proposed. As you know, that this is the only way a black hole can lose energy. But then if you work out the rate of Hawking radiation for a stellar mass black hole, for a black hole to lose all its mass due to Hawking radiation, the time scale is 10 to the power 60 years, 60, and the universe is only 10 to the 10 years old. So that tells you how faint the Hawking radiation is for stellar mass black holes. Now, in the early universe, things as mass was first forming, there is no reason to believe that the stars that formed then were the same as the stars that form now, because the density of matter was different, the pressure of matter, temperature of matter was different, and then natural collapse happens on a different scale. And if you are reading astrophysics, you will hear about Jeans masses and things like that. So these are natural things that come out of, and what is the natural scale and mass to collapse into objects. And in the very early universe, the conditions of the universe were very different. And if there were very supermassive objects that were formed then the Hawking radiation would actually be quite high. And so there are papers, including papers written by our students here at IUCAA who are working on this, that predict that from primordial black holes of a certain mass range, you can directly actually see X-rays or far ultraviolet radiation from them due to their Hawking radiation. Can be detectable, and people are trying to work out what kind of X-ray telescopes or UV telescopes would be needed to see them. Certainly something like this has not been seen yet.
Shashwata wants to know whether accretion disks form around all black holes?
If they're in a binary system, yes, because what will happen is, well, these accretion disks will shrink and get destroyed and build up again. It depends on the mass accretion onto them. The thing is, of course, it needs matter to fall onto a black hole to form these accretion disks. Now, the reason they form an accretion disk is, one, that as matter is falling onto them, it has its own angular momentum, so it can't fall straight in, just like the Earth is not falling into the sun because it has angular momentum, it's going around. And so, but if, for example, there's a black hole that's sitting there on its own and it's accreting matter from its surroundings, then it occurs at a rate where it can go straight into the black hole. It doesn't need to form an accretion disk. If it has a companion, which is a donor of matter, and a lot of matter to the black hole, then there's a lot of matter that's falling in. There's a limit to which a black hole can take in matter. It's called the Eddington limit. And it comes from the fact that as the black hole is accreting matter, it is also, as the matter is falling in, it gets very hot, and so it radiates. And this radiation comes out, the radiation has pressure. And the radiation that is coming out stops things from falling in. So there's an equilibrium between the amount of matter that's falling in and the radiation pressure. And this Eddington worked out quite in a different context, but it actually works for a black hole as well. And so there's only a finite rate at which matter can go inside a black hole. The rest just crowds around the black hole, forms an accretion disk, and rotates around it. And that you know, as the things fall in and the amount of radiation comes in, there's a balance between the two. So the accretion disk also grows and then shrinks and grows and shrinks and things like that.
Malikar is asking, why was the wavelength of 2 micrometer chosen particularly?
It was chosen because any shorter than that, the dust will stop it. The dust is, as you know, scatters, and so blue light is scattered more than red light. And as the wavelength increases, the amount of amount of light that can be stopped, scattered, absorbed by the dust, given the size of the dust grains, etc., is that you need to go at least 1.5 microns and higher in order for it to see through. So dust becomes transparent at that wavelength. And the second reason it is 2.2 microns is that is a window in the transparency of the atmosphere. As you saw, as you went beyond 1 micron, the water vapor in the Earth's atmosphere absorbs the infrared rays. And so you have to go very high in very dry places. Keck is in Hawaii, and Mauna Kea, very dry place at a height of 5,000 meters. And so there's very little water vapor above it. In Chile, it's of course, in the Andes Mountains, in the Atacama Desert, very dry place. In fact, where the telescope is, the VLT, I've been there quite a lot. San Pedro, which is the nearest village, has not seen rain for the last 200 years, right? And the driest place on the Earth is Antarctica. So there are infrared telescopes there as well. So you need a very dry place, and then you can see at 2 microns from the Earth. And that's why we can't launch a telescope that is 10 meters into space. That's huge. And so we need big telescope, but you have to observe through the dust. And this is why 2.2 microns is a very good choice.
I hope you can take a few more questions.
Yes, I'm here. Yes, go ahead.
Saumya Sarkar wants to know, what else can be studied using gravitational waves other than black hole mergers?
Well, so many things. I mean, gravitational waves come from almost everything, right? And of course, gravitational waves are not just one kind. We are now discovering gravitational waves that have a wavelength, that have a frequency of a hertz or 10 hertz or something like that. And so just like electromagnetic waves come from a whole range of radio, optical, infrared, and X-rays and gamma rays, gravitational waves has its own huge range. And so the LIGO detectors are built to detect gravitational waves in the range of 0.1 hertz to about 100 hertz maximum, and then the noise cuts off. There are other gravitational wave instruments that are being built in space as well as on the Earth, which will look at other wavelength ranges. But in this wavelength range, we have also discovered neutron star mergers. We've discovered 2 cases in which a black hole is merged with a neutron star to form another black hole. It, in principle, will detect supernova explosions, black holes where big stars have exploded. They also send out gravitational waves. We haven't detected them yet. There is something called the stochastic gravitational wave background, which is due to gravitational waves that are coming from all kinds of things. They all merge together to form a general background, and that should be detected at these frequencies as well. It's a big subject of research here in IUCAA of several PhD students working on estimating what kind of things can be observed. So this is because, I mean, we should be, even when you are moving around, you are emitting gravitational waves in space-time, but that's too faint. We started observing the most extreme ones, which are collisions of two neutron stars or two black holes. But slowly, as the sensitivity improves, we are going to look at anything. And that this is better than normal telescopes, because optical telescopes and electromagnetic telescopes are looking at electromagnetic disturbances. So these are only looking at things that have electromagnetic fields. Not all objects have electromagnetic fields, but everything has gravitation, right? So in principle, through gravitational radiation, you can find anything. And eventually, we should be able to detect the gravitational waves from the Big Bang itself. That's a different frequency range.
Srishti is asking, does all galaxies have a supermassive black hole at the center?
So a very, very good question. Our knowledge is that up to a certain mass, it seems that all galaxies have a supermassive black hole. That the limit of that mass is about 1/10 of the size of our galaxy. Our galaxy is pretty small. About things that are less than that, which are technically called dwarf galaxies, like, for example, the satellite galaxies that are moving around our galaxy, we know about 40 of them. They don't have supermassive black holes in the middle. They have something that's called a superstar cluster in the middle, which is maybe 10 to the 5, 10 to the 4 times the mass of the sun, but they are not compact objects. They are clusters of stars. But in the middle, having a supermassive black hole seems to be a property of what is known as giant galaxies, galaxies like us, or even things that are maybe about a 10th or a 50th of the mass of our galaxy, are much smaller. Small galaxies don't have.
Aditi has a question. So in 2018, there was one more observation by Muse, probably, the presence of moderate black hole at the center of globular cluster. Is that proved yet?
No, there have been many claims of measurements of what is known as intermediate mass black holes through X-rays, X-ray binaries, and through, for example, the Muse instrument is actually an instrument that is a two-dimensional spectrograph that looks at the center of a galaxy and has, from the spectral width of lines, tries to find the mass of the object, because it will cause the broadening of the line will be caused by gravitational redshift and Doppler redshift, things like that. And so you can try and measure the mass of the central object by the broadening of the spectral lines and things like that. But to do that, and of course also in X-ray binaries, you can measure the mass of the black hole, and there have been claims that people have found 1,000 solar mass black holes in them and things like that. But the problem is that these are very model dependent, and for every discovery, somebody else comes and shows that that is not the only explanation. There can be other things as well. And so there haven't been any unambiguous measurements before this 140 solar mass gravitational wave event of any black hole that is has a mass that's more than 50, 60 times the mass of the sun. And even then, in the last 5 years, these are all come from LIGO. The most massive black hole found from X-ray observations, unambiguously, without any doubt, is of the order of 20, 30 times the mass of the sun.
Mritika Ghosh wants to know, is an accretion disk essential to detect a black hole?
Well, you can detect quite a lot of things that are hot, that are, if they're 10 to the 7 degrees hot, they will emit X-rays. Around a black hole, the black hole does not have a surface. Things fall in. And so what will glow? So you need the accretion disk around it for it to get hot and glow in X-rays. If you're detecting a neutron star, for example, that has a surface. And you can detect the neutron star also if it's 10 to the 7 degrees hot, and it is in X-rays. And so, for example, in X-ray binaries, we can directly detect neutron stars, but we can't directly detect black holes. You will have to have something that is around it, that is close enough that it feels the gravitational potential energy of the black hole, which can heat it up to 10 to the 7 degrees. And the only thing that does it are these disks.
We will take two more questions. One is, why only matter distorts space-time? Why cannot field like electromagnetic field distort the space-time?
Why only matter distorts? Any energy can distort space-time. Matter and energy are the same thing, right? E equals mc squared. So in principle, mass energy, that is, can distort space-time. And so if you look at Einstein's equation of general relativity, and Dr. Scheinkar is going to talk a lot more about that when he talks about Penrose's work, is that the two sides of the equation that Einstein wrote down, one is the mass energy tensor, which essentially is, it tells you how much mass or energy there is in a particular object. And on the right-hand side, it gives you the geometry, the distortion in geometry, the change in geometry it causes space-time as a result. So it relates the two. So anything that is any confined object that has mass energy in space-time can cause a distortion in space-time. But of course, it has to have a field like like gravitation, right? So I can think of forms of energy that might not distort space-time. So Einstein has a prescription for what causes this distortion in space-time.
Thank you very much for your time. It was indeed a very exciting talk. Today, really enjoyed it. Thank you very much.
Thank you very much, and I'm very sorry about the technical hitches, and I'm glad a lot of people stuck with me till the end.
Yeah.
Thanks very much.
Thank you, Professor Somak. It was wonderful and excellent presentation. So happy to listen. I think definitely it's very, very inspiring. Maybe after the post-COVID era, we would like to invite you to our coordinates. Sometimes, thank you so much for your valuable
I'm very
time.
happy to come and visit you. I've been meaning to come and visit you in a long time. Let's start in-person visits, and I'm very happy to come and meet you and talk to you.
Thank you so much. Irrespective of your busy schedule of administration and other stuff, you could patiently listen to the questions and answering. So nice. Thank you so much. And I just want to have one more comment about the 37 numbers which you told, the first ever detection of gravitational waves. 2 of them are our MSc students.
Oh, that's wonderful.
Just want to thank you so much for your
excellent. And of course, you have Srinath there, who's also has a great experience of IUCAA, and I hope we continue to have a good relation between us. And I'd be very happy to see you introduce quite a lot of these astrophysics courses for your students. And I'm sure Srinath can help, and many others can.
Yeah.
Thank you.
Right. Thank you.
Thank you, sir.
Wow.
Okay, Sina, then we will just wind up this. You can, you can just